Hello everyone and welcome back to the Mammoth Interactive YouTube channel. It's Alex from Mammoth Interactive, and in this video we are going to do a visual approach to the SVM machine learning model, a very popular and famous machine learning model type. Before we jump into this video, go to the first link in the description because we're running a Kickstarter, Excel, machine learning, and blockchain in 99 days. Don't miss out. SVM, short for Support Vector Machine. So let's dive right in. The SVM model is popular because it works both on linear and non-linear data. And it's used for classification, for regression, clustering, and many types of machine learning problems, such as, for example, getting data points about any object like a mass or a patient and being able to classify them into a category like, is a mass a cancerous mass or a non-cancerous mass? Is a patient likely to develop heart disease or unlikely to develop heart disease? Let's get started. Let's say we have some data and it's labeled so we know what class it belongs to. For example, there's a bunch of data and it's a mass. So the researchers have collected data about a mass, and we're trying to determine, is this mass cancerous or non-cancerous? And the data set that you're training your model on has labels. But then if you get a new mass, you want to be able to quickly determine, is the mass cancerous or non-cancerous? So you start with your training data set where you have masses and you have them all labeled. But how do you find an algorithm that can separate these two classes with an algorithm, with a mathematical function? One answer is to draw a line that divides the two classes, and this line has a slope as well. It has an intercept, so you can write this line as a mathematical function. This is pretty logical, but there is a problem in that you can draw more than one perfect line to divide the classes. So you can have different mathematical functions that divide the classes perfectly. But that's a problem because the lines can be completely different. Some lines have a positive slope, some lines have a negative slope. So how do you know which line to choose? Because depending on the line that you choose, your results could be completely different on a new mass, because a new mass could be plotted somewhere on the chart based on features of it. And the new mass could be cancerous if you use one function, but non-cancerous if you use another function. So how do you know which line to use? Well, the answer is that SVM comes to the rescue. So instead of just drawing a line, we draw the possible lines and then we draw a margin around them. So the margin is the padding or the space around the line that you can draw without touching any of the points. You can touch the edges of the points, but the goal is to just get that distance, that space between the points. And you want to choose the line that has the largest margin. So this is known as maximum margin estimator. The line that you choose should be the line with that largest margin. That's how you know what's the best line, because that one can most separate the classes because it keeps the classes the furthest apart. Okay, so here's an example. We have a line and that represents the mathematical function. Then we have the dashed line, which represents the margin. Okay, and you'll notice that the margin can touch some of the points. These points are actually the key points in the data sample. So these masses that touch the margin of your plane here, these are known as the support vectors. These are the key vectors to the algorithm or the machine learning model, because these vectors actually determine the slope and the intercept as well. If you removed one of those points on the margin, your plane would actually completely change. So that's why SVM is called support vector machines, because it relies on these support vectors, these key masses, and all of the other masses are actually completely irrelevant because they're not part of the function. They're not touching the margin. If they're not touching the margin, they don't actually have an impact on the loss function or the machine learning model. So that's why SVM is called SVM. And take a look here. If you add more data points, our model doesn't actually change at all, because the only data points that matter are data points on the margin. Now, if you add data points that are inside of the plane or touching the margin, then that could change your machine learning model, because those data points are now the new margin. Those data points are now going to change the padding, the margin amount. So it all depends on where those new samples are added. But if you add new samples outside of the plane, outside of the margin, then your model actually doesn't change at all. You still have the exact same model, which you can see here. You have the exact same line, even though you have a different number of samples. So that shows you how important these support vectors are. Now let's take a look at nonlinear data, because we saw previously our data was linear. We could draw just a line, nice little line to separate the two classes. But here's a much more complex problem. What if you have, again, masses that you have labels, these masses are cancerous, these masses are non-cancerous, and you want to train your model to be able to detect on a new mass, is it cancerous or non-cancerous, based on its training on your labeled data. Well, how do you do that if your model here is nonlinear? Because there's no way to draw a perfect little straight line with a ruler through this data. This data, you have your blue class on the outside, it's in a circle, you have a circular blob in the center of your second class. So how do you separate this data with a mathematical function? Because the mathematical function, you can imagine, would look like a circle. You would have to separate these samples, the blue from the red, so you'd have to draw a circle to separate the two. How do you represent that with math? The answer is you can actually add another dimension to your data. So your data, it seems two-dimensional because you plotted it on a chart based on its features, feature for X, feature for Y. But you can actually add a new dimension and make your data 3D. And this is done with a mathematical function, and SVM abstracts a lot of that away for you, so it makes it really easy for you to take 2D data and make it 3D. And it sounds really complex, and luckily for us, SVM does abstract away a lot of the complexity. So you can transform your data from 2D to 3D, and you're still preserving the data features. It's not like you're actually changing the data set itself. You're just representing it in 3 dimensions. It's hard to wrap your head around, but stay with me here. You represent the data in 3 dimensions by using a mathematical function that you alter the data a little bit, but you still are keeping the data, the core data features, the core data representation. The reason you want to represent your data in 3D is because now you actually do have a nice little line that you can draw through the data. Now the line is now a 2D plane because you've added an extra dimension. So instead of drawing a nice little line, you just put a nice little piece of paper to separate these two samples in your head, of course. Because you can see now our red class is up top and our blue class is on the bottom. So now we actually can separate our data linearly. And that's the power of SVM. That's why it's so famous, popular, because SVM makes it easy for you to separate data linearly, even when originally it did not look like it was possible. Remember, originally we were looking at our data and we saw, oh, we have to draw a circle to separate the two classes. But now we have a linear way to separate the data. Okay, and you can then take that circle and put it back into 2D. So you can take your 3D representation, you then have that equation to divide your two classes with a linear line. But then when you bring that back to 2D, when you bring it back from 3D to 2D, it now looks like a circle. Okay, so it's hard to wrap your head around because you're going from 2D to 3D and then back to 2D. But this circle, it represents the algorithm for the machine learning model. So that circle that you're drawing, not a perfect circle, of course, but that circular shape that you're drawing, that is the machine learning model's function just represented visually. And when that circle is represented in 3 dimensions, it looks more like a piece of paper. But when it's represented in 2 dimensions here, it looks like a circle. And you still have the margins, because note that the dashed lines, those are the margins. Okay, so that solid line is the machine learning algorithm. The dashed lines are the margins. So you still have support vectors. This is still SVM. You still have those support vectors on which the whole model is dependent. But now you're just using SVM for non-linear data, and that's why SVM is popular. As well, you can use SVM for more than 2 classes. You can use it for multiple classes. Perhaps you have 3 different categories of a species that you're trying to classify your data samples into 3 species, well, you can do that as well. So SVM is quite powerful. It's usually great for when you have small data sets and there are few outliers. If you have large data sets or you have a lot of outliers, you're better off with another model like neural networks or something. It all depends on your data set and your goal. And that is the SVM model, explained visually. Don't forget to check out our Kickstarter first line in the description where you can learn a lot more about Python.